Welcome to this lecture titled Knowledge Types and Forms. In this lecture, we will explore the various ways knowledge can be classified, focusing on its purposes and forms of materialization. We will discuss different knowledge types based on their purposes and how knowledge forms are classified according to their materialization. In other words, where and in what shape they exist. Additionally, we will cover the 4 types of artifacts as defined in design science: constructs, models, methods, and instantiations. We will also delve into the concept of theories, which aim to explain objects and their relationships, often through cause and effect, and sometimes predict future events. Lastly, we will examine design theories, which systematize the knowledge about an artifact. To conduct a design science project, you need to understand its main components, the object of study and the 2 primary activities involved. The object of study is an artifact in context, while the 2 primary activities are designing and investigating this artifact in context. For the design activity, it is crucial to understand the social context of the stakeholders and the goals of the project. This context is the source of the research budget and the target for the useful research results. For the investigative activity, it is essential to be familiar with the knowledge context of the project. You will utilize this knowledge and contribute to it. Together, these 2 activities and their respective contexts create a framework for design science. This framework illustrates that the knowledge used and produced in design science is not universal but has a middle-range scope. Middle-range theory is a type of theory that falls between the minor but necessary working hypotheses of everyday life and the all-inclusive systematic efforts to develop a unified theory that explains all the observed regularities of social behavior, social organization, and social chains. In other words, it is a theory that addresses specific phenomena or concepts, providing a bridge between empirical observations and broad, abstract theories. Middle-range theories are characterized by their specificity and their ability to be tested and validated through empirical research. They are often used in fields such as sociology, nursing, and education to develop practical applications and interventions based on observed data. Scientific research generates various types of knowledge, with many attempts to classify these types over time. One of the earliest was Kant's distinctions between a priori versus a posteriori and analytic versus synthetic knowledge. Knowledge can be categorized into 6 types based on its purpose. This classification is based on a broad definition of knowledge. As described by Wikipedia, knowledge is a familiarity, awareness, or understanding of someone or something, such as facts, information, descriptions, or skills, which is acquired through experience or education by perceiving, discovering, or learning. Knowledge can refer to a theoretical or practical understanding of a subject. It can be implicit, as with practical skill or expertise, or explicit, as with a theoretical understanding of a subject. It can be more or less formal or systematic. Another method of classifying knowledge is based on its form of materialization. This is especially relevant in design science, as the knowledge produced can be implicit, often embedded within artifacts, rather than always being explicitly stated. Knowledge can serve various purposes, such as describing, explaining, and predicting phenomena. Based on these purposes, different types of knowledge can be identified. Definitional knowledge encompasses concepts, constructs, terminologies, definitions, vocabularies, classifications, taxonomies, and other forms of conceptual knowledge. This type of knowledge can be formal and precise, such as the fundamental concepts of relational database theory, which include relations, attributes, functional dependencies, and multivalued dependencies. Definitional knowledge serves as a foundation for all other types of knowledge by providing the essential concepts needed to express that knowledge. We can see 2 examples of definitional knowledge below. Firstly, a right triangle is a triangle in which one angle is a right angle. Secondly, a black hole is a region of space from which nothing can escape. And finally, a relation is in third normal form within relational database theory if all of its attributes are dependent on the key, the whole key, and nothing but the key. These statements only define certain concepts but do not claim that right triangles, black holes, or third normal forms really exist. Such claims are made by descriptive knowledge. Descriptive knowledge involves describing and analyzing existing or past realities. This type of knowledge typically involves describing, summarizing, generalizing, and classifying observations of phenomena or events. For example, descriptive knowledge can assert that the majority of enterprise resource planning system users in a company are dissatisfied. It can also describe individual entities and events, such as the fact that Ericsson has invested in a new global enterprise resource planning system. Additionally, it may describe relationships among entities, providing an analysis, such as the modular composition of an enterprise resource planning system. Unlike definitional knowledge, descriptive knowledge includes statements that are claimed to be true, aiming to describe the world as is. Descriptive knowledge does not claim to provide explanations or predictions. It only describes reality. Examples of descriptive knowledge are the statements like, "The height of the Eiffel Tower is 300 meters," and "All swans are white." Explanatory knowledge provides answers to how and why questions, explaining how objects behave and why events occur. It extends beyond descriptive knowledge by not only describing and analyzing phenomena, but also offering explanations to enhance understanding. Explanations typically involve cause-effect chains, illustrating how events and outcomes are causally linked to underlying mechanisms and factors. For example, the increased acceptance of internet banking among the public can be partially explained by improvements in security infrastructures. High-level explanatory knowledge seeks to demonstrate how the world can be perceived from a specific viewpoint, often with the goal of challenging conventional assumptions and fostering a new understanding based on innovative theoretical perspectives. Some theories utilized for this purpose include structuration theory, actor network theory, and critical theory. For instance, critical theory can be employed to explain why information systems, initially introduced to enhance productivity, frequently evolve into tools for monitoring and control. On the other hand, explanatory knowledge, at a lower level, offers explanations for specific situations, detailing why and how particular events occur. For instance, the implementation of a reward system within an organization can significantly contribute to employees' acceptance of a new enterprise resource planning system. Explanatory knowledge provides explanations for events after they have occurred and cannot be used to predict future events. Below we present a few examples of explanatory knowledge. Humans have descended from other animals through the process of natural evolution. The earthquake in Japan in 2011 was a result of tectonic plate displacements. The failure to implement social software in the company was due to its authoritarian organizational culture. Predictive knowledge provides black box predictions, meaning it forecasts outcomes based on underlying factors without explaining the causal or other relationships between them. The primary goal of predictive knowledge is to achieve accurate predictions rather than to provide understanding. High-level predictive knowledge with broad generality is uncommon in the IT and information systems field. One of the few examples is a Kokomo model, which offers cost estimation for software development. Similar to explanatory knowledge, predictive knowledge can also exist on a lower level, where it forecasts outcomes in specific situations, such as predicting that the risk of failure for a particular software development project is above average. Below we can see two examples of predictive knowledge. The first example stated as, "The treatment of patients by physicians with unwashed hands may result in diseases," while the second example is stated as, "Heavy exposure to sunlight may result in skin diseases." These examples only predict certain outcomes without explaining them. Although explanations for these predictions exist today, they were not known at the time this knowledge was discovered. Explanatory and predictive knowledge provides both explanations and predictions. It forecasts outcomes and explains their relationships to underlying mechanisms and factors, often through causal relationships. This type of knowledge is prevalent in natural sciences. While less common in the IT field, there are examples such as the technology acceptance model and the model of information system success. Additionally, explanatory and predictive knowledge can be integrated into broader theories, such as general systems theory and the soft systems methodology. Examples of explanatory and predictive knowledge. Microorganisms can survive in dirt and infect people that come into contact with them. Exposure to the ultraviolet radiation of sunlight may cause a burn of the skin, which may result in skin diseases. These statements both predict potential outcomes and explain them by detailing the underlying mechanisms responsible for them. Prescriptive knowledge includes models and methods designed to address practical problems. Prescriptive models serve as blueprints for developing artifacts, while methods provide guidelines and procedures to help people work systematically when solving problems. Prescriptive models and methods have two parts. The first part is a model or method itself. The second part is a statement about a positive outcome from using the model or method. This statement is not an absolute judgment but a prediction that using the model or method will lead to desired effects for certain stakeholders. In this way, prescription is a specific type of prediction. Examples of prescriptive knowledge are: firstly, wash your hands before going to surgery so that the patient will remain healthy. Secondly, apply sun lotion before sunbathing so that you do not get burnt. And finally, develop your software system iteratively so that you can target your stakeholders' goals. You now know about the 6 different knowledge types, in other words being definitional, descriptive, explanatory, predictive, the combined explanatory and predictive, and finally the prescriptive knowledge type. These knowledge types play a crucial role in shaping theories. Definitional knowledge helps in establishing the foundational concepts and terminologies of a theory, ensuring clarity and consistency across its application. Descriptive knowledge provides detailed observations and descriptions of phenomena, forming the empirical basis upon which theories are built. Explanatory knowledge offers insights into the underlying mechanisms and causes of phenomena, helping to understand why things happen the way they do, thereby strengthening the theoretical framework. Predictive knowledge enables theories to forecast future occurrences or trends, adding practical value and testing the robustness of the theoretical constructs. Combined explanatory and predictive knowledge integrates explanation and prediction, allowing theories to not only describe and explain phenomena but also predict future outcomes, making them more comprehensive and useful. Prescriptive knowledge guides practical application by providing models and methods that can be used to achieve desired outcomes, thereby linking theory to practice and enhancing its relevance and utility. Together, these knowledge types contribute to the development, validation, and application of theories, making them more robust, comprehensive, and relevant to both understanding and addressing real-world problems. While knowledge types describe the purposes for which knowledge can be used, knowledge forms specify how it can be materialized. In other words, where it exists and in what shape. Knowledge forms are crucial for design science research, as it creates knowledge that is not only explicitly codified in documents but also embedded in artifacts. There are 5 different forms of knowledge. Firstly, explicit knowledge. Secondly, embodied knowledge. Thirdly, embedded knowledge. Fourthly, knowledge forms in craft and science. And finally and lastly, knowledge forms in organizations. For the next slides, I will discuss these briefly. Explicit knowledge is articulated, expressed, and recorded in media such as text, numbers, codes, formulas, musical notations, etc. Typical containers of explicit knowledge include textbooks and manuals. One of the main strengths of explicit knowledge is its ease of transfer between individuals, as it is stored in media that can be conveniently moved and decoded. However, not all knowledge can be articulated explicitly, such as practical skills, intuitions, and experiences. For example, reading a manual on how to juggle a football with your feet is not very efficient. Embodied knowledge, sometimes called tacit knowledge, is situated in the minds of people and is often difficult to formulate in an explicit way. Tacit knowledge refers to the kind of knowledge that is difficult to transfer to another person through writing it down or verbalizing it. It is the personal knowledge embedded in individual experience and involves intangible factors such as personal beliefs, perspectives, and value systems. Examples include practical skills, intuitions, and experiences, such as riding a bicycle, cooking a dish without a recipe, or diagnosing complex problems intuitively. Tacit knowledge is often acquired through personal experience and context, making it challenging to codify and share. Embedded knowledge resides in entities such as physical objects, processes, routines, or structures, rather than in humans. For example, consider a bread maker, a home appliance for making bread. When provided with the right ingredients, the machine can produce a loaf of bread by mixing the ingredients, kneading the dough, and baking it. By studying how the machine operates, one can learn about bread making. Therefore, the machine can be viewed as embedding the prescriptive knowledge of how to make bread. It contains a recipe, which is a method. In traditional crafts, design knowledge is often embedded within objects. This is not due to laziness, but because objects can capture the full richness and nuance of the design. Apprentices studying an artifact crafted by a master can gain a deep understanding of the design principles. This way, the knowledge of the master is transferred to the apprentice through the artifact. While embedding knowledge in artifacts offers depth and intuition, it has drawbacks. Learning by studying artifacts can be time-consuming, as seen with craft apprenticeships that take years. The knowledge gained depends heavily on the individual's background and learning style. Some may learn effectively, while others may not. Additionally, it is difficult to analyze, critique, and evaluate knowledge embedded in objects, as explicit knowledge is better for reflection and innovation. Design science aims to support designers and researchers in making design knowledge explicit, transitioning design from craft to science. It does this by clarifying design principles and providing methods for creating artifacts and explicit knowledge about them. However, not all knowledge can be made explicit, so the artifact itself remains an important outcome of any design science project. Knowledge in an organization can take various forms, embodied in individuals, explicit in documents, embedded in routines, and embedded in technology. Each form has its own pros and cons for knowledge retention and transfer within the organization. Knowledge in individuals. Employees are key holders of organizational knowledge. They can explain their work methods and reasons in a way that suits the listener's understanding. However, they might protect their knowledge for personal gain. They can be overwhelmed with questions, and their departure can lead to a loss of knowledge. Knowledge in documents. Information about goals, plans, and processes can be stored in documents like business plans and budgets. This form of knowledge is easily accessible and can be analyzed, but documents might be hard to find, interpret, and keep up to date. Knowledge in routines. Organizational routines and standard procedures effectively store and transfer knowledge over time. New employees can learn these routines from colleagues, ensuring knowledge continuity. However, routines can become outdated or hard to change, especially when the external environment shifts. Knowledge in technology. Technology, like IT systems, can enforce standardized ways of working and is an effective way to store and transfer knowledge. However, changing technology can be costly and time-consuming, potentially hindering necessary changes. When developing an artifact, such as an IT system, in a socio-technical environment, designers must understand the existing knowledge and how it is represented. They need to decide what knowledge the artifact will represent and how it will impact the organization's work processes and knowledge transfer. There is a risk that new systems or methods could disrupt effective existing practices, hindering efficiency, innovation, and quality. Artifacts can be classified in various ways based on the type of knowledge they convey and whether the knowledge is explicit or embedded. Additionally, they can be categorized according to their function and use. Within design science, It has become well established to identify 4 types of artifacts, being constructs, models, methods, and instantiations. Constructs are terms, notations, definitions, and concepts essential for formulating problems and potential solutions. They do not make statements about the world but enable us to discuss, understand, and change it. Therefore, constructs represent definitional knowledge and are the smallest conceptual atoms for understanding and communicating about various phenomena. Examples for constructs could include the concept of a class in the Unified Modeling Language, a method in Java, functional dependency in relational database theory, and affordance in human-computer interaction. Models are representations of potential solutions to practical problems and can support the construction of other artifacts. For instance, a drawing can guide the building of a house, and a database model can assist in developing a database system. Since models prescribe the structure of other artifacts, they express prescriptive knowledge. A model is composed of interconnected constructs. Methods convey prescriptive knowledge by outlining guidelines and processes for solving problems and achieving goals. Specifically, they can prescribe how to create artifacts. Methods can range from highly formalized, like algorithms, to informal, such as rules of thumb or best practices. Examples include methods for database design, change management initiatives, and web service development. Instantiations are functional systems that can be used in practice. They often embed knowledge, such as a database embedding a database model. Examples of instantiations include a Java program implementing a search algorithm, a database for electronic medical records, or a new planet in the computer game Entropia. In design science, the concept of a model is more specific than in other fields. Generally, models are categorized into 4 types: descriptive models that describe existing situations, explanatory models that explain observed situations and patterns, predictive models that forecast behavior, and prescriptive models that propose solutions to problems. These models represent different types of knowledge, but only prescriptive models are considered artifacts. An instantiation, defined as a working system used in practice, must be based on another artifact, serving as a template or idea. Constructs are too small to be working systems, but models, like blueprints and architectures, can be instantiated. The question arises whether methods can also be instantiated. While applying a method results in a working system, the system itself is not an instantiation of the method. Instead, the instantiation of a method consists of the actions and events during the system's development, which don't qualify as a working system. Some argue that the definition of instantiation is too narrow and should include method applications. Methods are complex and context-dependent, and some knowledge is embedded in their application, which can be communicated through videos or notes. However, transferring knowledge through method applications is challenging, especially over long periods. In certain fields, like physiotherapy, method applications could be useful artifacts. For example, a short video of an innovative exercise can effectively transfer knowledge. Another method of classifying artifacts is by their function. Here is a suggestion for categorizing IT application instantiations into 7 archetypes based on the roles they serve for their users. Since the archetypes are ideal types, a single IT application can fall under multiple archetypes. For instance, an email system is primarily designed to mediate communication, but it can also be used as a personal information storage, thereby functioning as an information source. Another way of classification of artifacts is to use 8 artifact classification types, which basically introduce 8 artifact types. Below we can see them. System design, a structure or behavior-related description of a system, typically using text and some formal language. Method, a definition of activities to create or interact with a system. Language notation, a system to formulate statements about some domain. Algorithm, an executable description of system behavior. Guideline, a suggestion regarding behavior in a particular situation. Requirements, a statement about required behavior and functions of a system. Pattern: a definition of reusable design elements with their benefits and application context. Metric: a mathematical model able to measure aspects of systems or methods. It can be argued that this classification accurately reflects what IT and information systems practitioners recognize as key types of artifacts. Therefore, for this domain, it can be considered more practical and easier to apply than the more abstract classification of constructs, models, methods, and instantiations. Theories are essential for organizing and structuring large amounts of scientific knowledge. According to Encyclopaedia Britannica, a scientific theory is a systematic, broad structure created by human imagination that includes a set of empirical laws about regularities in objects and events. It aims to explain these laws in a rational manner, often through cause and effect relationships, and can sometimes predict future events. An example is agency theory, which addresses conflicts between individuals with different interests in the same assets. For instance, company owners may have different interests than their managers. Key constructs in agency theory include principle, agent, risk, goal, contract, and monitoring. The theory makes descriptive statements like agents often do not act in the interest of their principals, explanatory statements like agents do not always act in the interest of principals due to differing goals, and predictive statements like monitoring may improve the efficacy of behavior-based contracts. Thus, agency theory describes, explains, and predicts phenomena in agency relationships. Theories can vary in scope between grand theories, middle-range theories, and micro-range theories. Grand theories are comprehensive, abstract, and aim to explain a wide range of phenomena, such as Marxism, functionalism, psychoanalysis, and structuration theory. Middle-range theories explain phenomena at an intermediate level across different contexts, such as agency theory and the technology acceptance model, which predicts how users accept and use technology. Micro-range theories address specific phenomena in particular settings, like patient care in urban hospitals. The distinction between middle-range and micro-range theories is mainly about the degree of generality. In design science, many contributions are similar to micro-range theories, where specific artifacts are developed and evaluated in particular practices. More abstract and mature design knowledge can be organized as middle-range design theories. Design science research aims not only to produce an artifact, but also to generate knowledge about it. When this knowledge becomes mature and comprehensive, it can be organized into a design theory. Expressing design knowledge as a theory makes it explicit and systematic, enabling it to be used and extended in the cumulative development of knowledge. A design theory structures the knowledge about an artifact through 8 elements: purpose and scope, the set of requirements or goals that specifies the type of artifact to which the theory applies and in conjunction also defines its scope and boundaries. Constructs, representations of the entities of interest in the theory. These entities can be physical as well as abstract. Principle of form and function, the abstract blueprint or architecture that describes an artifact. For a model, its components and their relationships and functions would be described. For a method, its steps and their order and purpose would be given. Artifact mutability, the changes in the state of the artifact anticipated in the theory. In other words, the degree of artifact change encompassed by the theory. Testable propositions, testable propositions about instantiations of the artifact under consideration. Typically, these propositions state that if a model or method is instantiated, then it will work, or it will have certain characteristics. Justificatory knowledge, the underlying knowledge or theories that provide a basis and justification for the design. Principles of implementation, processes for implementing, in other words, instantiating, the artifact to which the theory applies in specific situations. Expository instantiation, an implementation of the artifact that can assist in representing the theory both as an expository device and for purposes of testing. An instantiation can support communication about the artifact of a design theory. These elements collectively ensure that the design theory is comprehensive, systematic, and applicable, facilitating the cumulative development of knowledge regarding a system. In this lecture, we have talked about how knowledge can be classified in different ways. For example, based on purposes and different ways to materialize the knowledge. Knowledge types classify knowledge based on its different purposes. Knowledge forms classify knowledge based on its materialization. In other words, where it exists and in which shape. There are 4 types of artifacts, according to a well-established categorization within design science: constructs, models, methods, and instantiations. A theory aims to explain objects and their relationships, typically through cause and effect relationships. Sometimes, a theory can also be used to predict future events. A design theory is a theory that systematizes the knowledge about an artifact. This lecture is based on the contents from the book An Introduction to Design Science by Johannesson and Purgens. For more in-depth reading, you can read and study Chapter 2 Knowledge Types and Forms.